Everyone, today we are going to see about Hahn-Banach theorem. So, if M is the linear subspace of the non-linear space, M is the linear subspace of the normed linear space N, let F be the functional defined on M. F is the functional defined on M. Then F can be extended to the functional F naught defined on the whole space N. F naught is defined on the whole space. We have to extend the f to f naught defined on the whole space on n such that both the term norm f equal to norm f naught. Okay, first, now m is the given linear subspace of n. By the above lemma we know that the lemma given here is hmm? M be the linear subspace of the normed linear space n. Let F be the functional defined on M. So x naught is a vector not in M, and if M naught equal to M plus x naught is the linear subspace spanned by M, and x naught spanned by M and x naught. M naught is the linear subspace spanned by M and x naught. Then F can be extended to the functional F naught defined on M naught such that norm F naught equal to norm F. For that, uh, by the above lemma, we know that x belongs to, there exists a non-zero vector which is x belongs to n and x does not belongs to m. We can extend the functional f on m plus x to the whole space. There we take x naught as a non-zero vector, here we take x as a non-zero vector, so we can extend the function f on m plus norm x such that it preserves the condition for such that it preserves the condition norm f equal to norm f naught. So we take here norm f is the preserved for extension. So we have to consider the set of all possible extension of, what are the possible extension of f? We have to consider on all the subspaces. What are the possible extension of f on all subspaces? We have considered that m plus set of any other elements of n not in m of n which contains n which contains m. We have to take that m plus element which are not present in, which are present in n and not in m. So the set of extension of f, so we take the set of extension as g. The set of extension of f says g can be partially ordered. So the set can be partially ordered. Partially ordered means it should satisfy the reflexive, antisymmetry and transitive. Let g1 to g1 be belongs to g. We define the relation that is less than or equal to by saying g1 is less than or equal to g2, means that domain of g1 is, the domain of g1 is contained in the domain of g2, and g1 of x equal to g2 for all, g1 of x equal to g2 for all x belongs to the domain of g1. So g less comma less than or equal to is the partially ordered set. We denote it as a partially ordered set. So it should satisfy the reflexive, antisymmetry and transitive. So for g1 less than or equal to g1 for all g1 belongs to capital G and on the set. Let antisymmetry is g1 less than or equal to g2 and g2 less than or equal to g1. So domain of g1 is contained in the domain of g2 and domain of g2 is contained in the domain of g1. So both domain of g1 is equal to the domain of g2. Next, what we have to means g1, which is g1 of x equal to g2 of x for all in the domain of g1, g2 of x equal to g1 of x for all x in the domain of g2. So antisymmetry, difference between symmetry and antisymmetry is, we have to say that symmetry is a less than or equal to b and b less than or equal to a, but in antisymmetry we have to show that a less than or equal to b less than or equal to a, then a equal to b. So g1 equal to g2 as the domain are same and the functional values are equal for all points of the domain. If the domain are same means and the functional values are equal for all the points of the domain. So transitivity, let g1 is less than or equal to g2 and g2 is less than or equal to g3. So the domain of g1 is contained in the domain of g2, which is g1 of x equal to g2 of x for all x in the domain of g1, and the domain of g2 is contained in the domain of G3 for G2 of x equal to G3 of x for all x in the domain of G2, and hence for all x in the domain of G1 as the domain as of the G1 is contained in the domain of G2. So the domain of G1 is contained in the domain of G3. G1 of x equal to G2 of x for all x in the domain of G1. So G1 of x is less than or equal to G3. All the conditions are satisfied. So G is a partially ordered set. The set G1, G is not only a partially ordered, but every chain in G has an upper bound. So G is not only partially ordered, but every chain of G has an upper bound. So let G dash be the chain. We take that G dash be a chain in G. The union of domains of G's belongs to, all the unions of the domains of G's belongs to G dash. So we take the chain in G dash, and all the union of domains of G's belongs to G dash. In the G dash is the domain of upper bound of the elements in D. G dash is the domain of, G dash contains the domain of upper bound of elements in G dash. Then every chain in G has an upper bound. So every chain in G has an, whatever the chain in G has an upper bound. So by Zorn lemma, there exists by Zorn lemma means if there are partially ordered set, every total ordered subset has an upper bound, then the set has an maximal element. So partially ordered set is this every totally ordered subset has an upper bound and the set has a maximal element, and the ordering is just by the relation like A less than or equal to B, B less than or equal to C, A less than or equal to C, B, A less than or equal to B, B less than or equal to A equal to B. So it has a maximal element. Likewise, a Zorn lemma, there exists a maximum element in G. Say F naught, and now we want to show that F naught is the, so the maximal element taken here is F naught. We want to show that F naught is the required extension of the whole of n. We have to show that the maximal element is the required extension of the whole space n. So then it is not, if it is not a maximal element means then there exists a vector, non-zero vector, which is x belongs to n and not in m, which is not present in m. There exists a non-zero vector in n. So F naught can be extended to the domain. For that, F naught can be extended to the domain of F naught plus x based on the lemma m plus x, okay, based on the previous lemma. But we take F naught is the required extension, but we get here as F naught plus x. This violates the maximality of F naught. So F naught is the required extension of F to the whole space of n, such that norm F equal to norm F naught. Hope you all understand. Thank you.